December 3rd, 1944. 3rd Armoured Division Maintenance Area, Belgium. Sergeant Frank Durbin wiped hydraulic fluid from his hands and stared at the disabled Sherman that had just rolled into his repair bay. The transmission had failed completely. 48 hours ago, this same failure would have meant sending the tank back to a depot 200 miles away, leaving it out of action for weeks. Preparing and narrating this type of story took us long efforts and hard work, so if you are enjoying the story, please consider subscribing to our channel. Now Durbin's crew had the tank's entire power pack out, a replacement installed, and the Sherman rolling back toward the front in under 4 hours. The German Panther that his unit had captured last month, that same repair would take 3 days, require splitting the hull, and demand specialized tools that existed only in factory settings. American tankers called it wasteful. They called it over-engineered. They said the Sherman's modular design used twice as much steel and 3 times as many fasteners as necessary. German engineers who examined captured Shermans dismissed the approach as typical American excess, building tanks like they were assembling trucks on a factory floor. What none of them understood that cold December morning was that this wasteful design philosophy, this seemingly inefficient approach to tank engineering, was about to prove more valuable than armor thickness, more crucial than gun caliber, more decisive than any single technological advantage. The Sherman wasn't designed to be unrepairable. It was designed to be repaired by ordinary mechanics with ordinary tools in extraordinary circumstances. And in doing so, it would revolutionize how armies thought about armored warfare itself. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The story begins not on a battlefield, but in a design office in Detroit, 1941. The Rock Island Arsenal had just delivered its assessment of tank manufacturing to Army Ordnance. The report was damning. Current production methods treated each tank as a custom-built weapon system. Components were hand-fitted. Tolerances varied. 2 tanks rolling off the same production line could have parts that weren't interchangeable. This approach made sense in peacetime, when the United States Army owned exactly 66 medium tanks and produced perhaps 3 per month. It made no sense at all when facing the possibility of war against Germany, which had already deployed over 3,000 panzers across Europe. The Ordnance Department approached the problem from a military perspective. They wanted better tanks, more advanced tanks, tanks that could match or exceed German specifications. Chrysler Corporation's engineers, fresh from transforming the Detroit tank arsenal into a production marvel, saw a Chrysler Corporation marvel, different problem entirely. The issue wasn't building better individual tanks. The issue was building adequate tanks in numbers that made individual superiority irrelevant, and then keeping those tanks operational despite the chaos of combat. This required abandoning every assumption about how military equipment should be designed. Traditional tank design followed a craftsman model. Each major component, the engine, the transmission, the final drives, was installed during hull construction and effectively became part of the tank's structure. Removing a failed transmission meant partially disassembling the tank itself. This approach minimized weight and maximized armor protection by making every cubic inch of interior space serve multiple purposes. It also meant that field repair was nearly impossible. When a transmission failed in a German Panther, recovery crews had to tow the 30-ton vehicle to a depot facility. Mechanics would remove the turret using overhead cranes. They would then split the hull into 2 sections. Only after this massive disassembly could they access the transmission. The entire process required 10 to 12 hours of work by highly skilled technicians using specialized equipment. The Americans looked at this and saw a fatal flaw. In mobile warfare, time determined everything. A tank disabled for 2 weeks represented not just lost combat power, but lost opportunity. Every day that tank sat waiting for repair was a day it couldn't support an advance, couldn't defend a position, couldn't influence the battle. Chrysler engineer Owen Skelton proposed a radical alternative. Instead of integrating components into the hull structure, design them as modules that could be removed and replaced as complete units. This meant accepting significant trade-offs. Modular design required more internal space, which made the tank taller and increased its profile. It required more fasteners, more access panels, more structural reinforcement around mounting points. All of this added weight without adding armor or firepower, but it meant a failed transmission could be swapped in hours rather than days. A damaged engine could be replaced with a spare without requiring crane facilities. Worn-out final drives could be unbolted and swapped by mechanics working in field conditions with hand tools. The Army Ordnance Department initially rejected the concept. Their objection was straightforward. Every pound devoted to ease of maintenance was a pound that couldn't be armor or ammunition. The Sherman's modular design made it heavier than it needed to be for its armor thickness and gun caliber. German tanks achieved superior protection using less total weight because they didn't waste mass on accessibility features. Skelton's response would prove prophetic. A tank that can't be repaired is a tank that's permanently disabled the first time any component fails. You're not building tanks, you're building disposable weapons that work until something breaks. By mid-1941, Sherman design specifications reflected a compromise between military requirements and manufacturing reality. The hull would be constructed from large castings or welded plates, depending on the manufacturer. This allowed multiple producers to use whatever fabrication methods their facilities supported. The powertrain, engine, transmission, and related components would be designed as a removable assembly. The Continental radial engine, borrowed from aircraft production, would mount on a structural frame. This frame would bolt to the hull at 6 points. Removing these 6 bolts and disconnecting fuel lines, electrical connections, and drive shafts allowed the entire power pack to be extracted through the rear of the hull. This design decision had profound implications. It meant Sherman hulls could be produced without waiting for engine availability. It meant engines could be tested and certified before installation. It meant a disabled tank in the field didn't need a new engine installed in place. It needed the entire power pack swapped as a unit. The same philosophy extended throughout the design. The vertical volute spring suspension system, borrowed from earlier American light tanks, used bogie assemblies that bolted to the hull. Each bogie contained 2 road wheels, suspension arms, and a return roller as a complete unit. A damaged bogie could be unbolted and replaced in under an hour. The tracks themselves were designed for field replacement. Each track block connected to the next using pins that could be driven out with a hammer and punch. German tank tracks often used pressed pins or welded connections that required specialized tools to service. Sherman tracks could be repaired by any crew member with basic tools. Even the turret reflected this accessibility philosophy. It mounted on a large diameter ring bearing that allowed it to be lifted off the hull with simple rigging. This wasn't necessary for normal operations, but it meant depot facilities could swap damaged turrets onto repaired hulls, essentially rebuilding complete tanks from salvaged components. Critics pointed out that this approach created vulnerabilities. The large rear doors required to remove the power pack were thinner than side armor. The access panels for electrical systems and hydraulics created potential weak points. The suspension bogie mounts concentrated stress at specific points rather than distributing it across the hull structure. All of this was true. It was also irrelevant to the actual problem the Sherman needed to solve. The tank wasn't designed to be invulnerable. No tank is invulnerable. It was designed to be operationally available despite the normal wear, tear, and battle damage that every combat vehicle experiences. The first Sherman rolled off the Lima Locomotive Works production line in February 1942. By June, monthly production exceeded 300 tanks. By December, over 2,000 Shermans per month were being delivered to Army units. This production rate would continue throughout the war, ultimately producing approximately 50,000 Sherman tanks across all variants. But production meant nothing without the second crucial element. The Army needed to fundamentally change how it thought about tank maintenance. This led to the development of the 5-echelon maintenance system, a revolutionary approach that would define American military logistics for decades. First echelon maintenance was performed by the tank crew themselves. This included daily inspections, fluid checks, track adjustment, and minor repairs. Every crew member received basic mechanical training. The driver and assistant driver were expected to handle most routine maintenance without outside assistance. Second echelon maintenance was performed by the unit's organic maintenance section. Each tank company included a maintenance platoon with dedicated mechanics, specialized tools, and a small inventory of spare parts. These mechanics handled repairs beyond crew capability, replacing damaged components and performing scheduled maintenance that required more than hand tools. Third echelon maintenance occurred at the battalion level. Ordnance medium maintenance companies were attached to armoured divisions, providing workshop facilities that could handle major repairs. These units could replace entire powertrains, rebuild transmissions, patch armour damage, and return disabled tanks to service within days rather than weeks. Fourth echelon maintenance operated at the Army level. Ordnance heavy maintenance companies provided depot-level capabilities in the field. They could perform complete rebuilds, manufacture repair parts that weren't available through supply channels, and handle damage that would have required factory return under traditional systems. Fifth echelon maintenance occurred at fixed depot facilities in the rear areas or back in the continental United States. These facilities performed complete overhauls, major modifications, and handled damage beyond field repair capability. This system worked because Sherman design supported it. A third echelon maintenance company couldn't rebuild a Panther transmission in field conditions because the Panther wasn't designed for field maintenance. But they could swap a complete Sherman power pack because the Sherman was explicitly designed to make that possible. The system also required a massive logistics infrastructure. Spare power packs had to be positioned where they'd be needed. Replacement bogie assemblies had to be stocked at appropriate echelons. The supply system had to track thousands of unique part numbers and ensure availability across multiple theatres of operation. By late 1942, the system was operational but untested. North Africa would provide the first real-world stress test. The results would validate the entire approach and expose critical weaknesses that required immediate correction. British forces received the first Shermans deployed to combat in October 1942. The tanks arrived at the Second Battle of El Alamein, where they immediately proved superior to the German Panzer III and IV tanks they faced. The 75mm gun could penetrate most German armour at combat ranges. The reliability was exceptional compared to British tanks that had suffered constant mechanical problems in desert conditions. But the real advantage emerged after the battle. British armoured units had learned brutal lessons about tank availability. Crusader and Valentine tanks frequently spent more time under repair than in combat. Supply problems meant waiting weeks for spare parts. Mechanical complexity meant repairs required specialized facilities. Sherman maintenance proved dramatically different. When a tank threw a track, the crew could usually repair it in under 2 hours, using tools carried on the vehicle. When a final drive failed, battalion maintenance could replace the entire unit in a single day. When an engine failed, third echelon maintenance could swap the power pack and return the tank to service, while the failed engine was sent to the rear for rebuild. The operational availability rate told the story. British armoured units equipped with Crusaders typically maintained 40 to 50% availability. Units with Shermans sustained 70 to 80% availability despite identical combat conditions. This meant a regiment with 60 Shermans could typically field 48 operational tanks. A regiment with 60 Crusaders might field only 30. The Americans learned similar lessons in Tunisia during Operation Torch. The 1st Armoured Division landed in November 1942 with 163 Sherman tanks. By January 1943, after 2 months of combat, 98 remained operational despite casualties and mechanical failures. The division's maintenance companies were recovering disabled tanks, repairing them in field conditions, and returning them to combat in days. German intelligence reports from this period reflect confusion about American maintenance capabilities. German units reported destroying specific Sherman tanks, only to encounter what appeared to be the same vehicles days later. The Germans initially suspected the Americans had far more tanks than intelligence suggested. The reality was simpler. The Americans were repairing and returning damaged tanks faster than German planners thought possible. The Sicily invasion in July 1943 provided more extreme conditions. Combat in mountainous terrain produced constant mechanical stress. Tracks wore out rapidly on rocky roads. Suspensions failed from hard use. Engines overheated in summer heat while hauling maximum loads up steep grades. 2nd Armoured Division maintenance records from Sicily document the effectiveness of modular design. The division's tank battalions replaced 114 powertrains during the 38-day campaign. These weren't depot-level overhauls. These were field replacements performed by battalion and regimental maintenance companies operating from improvised workshops. Under traditional maintenance doctrine, 114 disabled tanks would have been evacuated to depot facilities for engine replacement. The tanks would have been out of action for weeks. Under the echelon system, using Sherman modular design, most were returned to service within 48 hours. Track replacement provided another dramatic example. German tanks used pressed pins to connect track blocks. Replacing damaged track sections required hydraulic presses that existed only in workshop facilities. Sherman tracks used simple drive-out pins. A crew with a hammer, punch, and replacement track blocks could repair moderate damage in 2 to 3 hours. This seemingly minor detail had major operational impact. German tanks that threw tracks in forward areas often had to be towed to maintenance facilities, even if the tank itself was undamaged. Sherman tanks that threw tracks were usually repaired where they sat and returned to combat the same day. By autumn 1943, Allied forces were preparing for the Italian campaign. Terrain in Italy would prove even more challenging than Sicily. Mountain roads, winter weather, and intense combat would stress every aspect of tank design and maintenance capability. The lessons from North Africa and Sicily led to several critical modifications. The Army expanded organic maintenance capability at the battalion level. Additional maintenance companies were activated and attached to armoured divisions. The supply system improved spare parts availability, particularly for high-wear components like tracks, bogies, and powertrains. But the fundamental advantage remained the Sherman's design philosophy. Every engineer who worked on the tank had prioritized one question above all others. Can this component be accessed, removed, and replaced by mechanics working in field conditions with standard tools? This question shaped thousands of design decisions. It determined how the hull was constructed. It influenced armor layout. It dictated internal configuration. And it meant that when Staff Sergeant Frank Durbin faced that disabled Sherman in Belgium in December 1944, he had a tank designed to support exactly what he needed to do. The operation Durbin performed that day wasn't extraordinary by Sherman standards. It was routine. That routine nature represented the real revolution. Tank maintenance had been transformed from specialized craftsmanship requiring factory facilities into standardized procedures that could be performed anywhere by anyone with appropriate training and the right tools. The Italian campaign revealed the full implications of American maintenance philosophy. Fifth Army maintenance records from Anzio document repairs that would have been impossible under traditional doctrine. Tanks disabled by mine strikes had their suspensions rebuilt in forward positions. Vehicles with catastrophic engine failures received replacement powertrains while German artillery continued falling around the maintenance areas. Technical Sergeant James Morrison of the 7th 156th Tank Battalion kept detailed notes throughout the Italian campaign. His account, preserved in the National Archives, provides extraordinary insight into how the maintenance system actually functioned under combat conditions. Morrison's unit operated M4A3 Shermans equipped with the Ford GAA V8 engine. This power plant produced 450 horsepower and was specifically designed for ease of maintenance. Ford engineers had prioritized accessibility over compactness, resulting in an engine that was larger than necessary but could be serviced by mechanics with minimal training. Preparing and narrating this type of story took us long efforts and hard work. So, if you are enjoying the story, please consider subscribing to our channel. In January 1944, Morrison's battalion sustained heavy combat losses near Cassino. 14 tanks were disabled by enemy action. 5 had sustained engine damage from fires after penetrating hits. 3 had thrown tracks and damaged suspension components after hitting mines. 6 had mechanical failures, including transmission problems and final drive failures. Under pre-war doctrine, all 14 tanks would have been evacuated to depot facilities. Expected turnaround time would have been 4 to 6 weeks, possibly longer if parts availability was limited. Morrison's maintenance platoon returned 12 of the 14 tanks to operational status within 1 week. The process Morrison describes reveals how modular design enabled this. The 5 tanks with engine damage didn't receive in-place engine repairs. Instead, maintenance crews removed the entire power pack as a unit, installed replacement power packs from supply, and sent the damaged units to the rear for rebuild. Each power pack swap required approximately 4 hours with a 4-man crew. The 3 tanks with suspension damage had complete bogie assemblies replaced. Each Sherman carried spare bogie assemblies. Additional spares were stocked at battalion level. Replacing a damaged bogie required removing 4 bolts, disconnecting nothing else, and bolting the replacement unit in place. Time per bogie, 45 minutes to 1 hour. The 6 tanks with transmission and final drive failures presented more complex challenges, but the modular approach still applied. Transmissions could be removed without splitting the hull. Final drives bolted to the hull and could be replaced as complete units. These repairs took longer, 6 to 8 hours for transmission replacement, 3 to 4 hours per final drive, but they were performed in field conditions by battalion-level mechanics. Morrison's account emphasizes something that official reports often missed. The Sherman wasn't easier to repair because American mechanics were more skilled. It was easier to repair because every component was designed to be removed and replaced rather than accessed and rebuilt. This distinction was crucial. Rebuilding a component in place required diagnostic skills, specialized tools, and often improvised solutions when exact replacement parts weren't available. Swapping a complete module required following procedures, having the right replacement unit, and basic mechanical competence. The first approach demanded expertise. The second approach demanded logistics. The United States Army excelled at logistics. By mid-1944, the supply system could deliver spare powertrains to forward maintenance units with reasonable reliability. Bogie assemblies, track blocks, final drives, and other major components moved through the supply chain like any other commodity. This worked only because Sherman design treated these components as field replaceable modules rather than permanent structural elements. British maintenance officers who observed American procedures reported their findings to the War Office. The reports expressed astonishment at how quickly American units returned damaged tanks to service. One British liaison officer noted that a Sherman battalion could sustain 25% combat losses and return to full operational strength within 72 hours, assuming spare parts availability. No British armoured unit could achieve similar reconstitution rates. The secret wasn't superior American mechanical skill or better training. It was design philosophy. British tanks like the Cromwell featured sophisticated Christie suspension systems that provided excellent performance but required specialized knowledge to repair. Sherman suspension used simple vertical volute springs that any mechanic could service. British tanks used complex gearboxes that demanded precise adjustment. Sherman transmissions were designed to operate across wide tolerance ranges. The French campaign that began in June 1944 would stress the maintenance system beyond anything experienced in North Africa or Italy. Operation Overlord involved landing thousands of vehicles on contested beaches, supporting rapid advances across destroyed infrastructure and maintaining operational tempo, despite logistical challenges that defied pre-war planning assumptions. 3rd Armored Division landed on Omaha Beach beginning June 23, 1944. The division included 232 Sherman tanks distributed across 3 tank battalions and supporting units. Within 2 weeks, the division was engaged in the bocage fighting that characterized the Normandy campaign. Bocage terrain produced extraordinary mechanical stress. Narrow lanes forced tanks to push through hedgerows, stressing engines and transmissions. Rough fields wore out suspension components. Mine strikes were common. Combat damage from German anti-tank weapons disabled multiple vehicles daily. Division maintenance records for July 1944 document the scale of repair operations. The division's Ordnance Battalion processed 317 tanks through second echelon maintenance or hire. This included 68 power pack replacements, 143 suspension repairs, 92 transmission or final drive replacements, and 14 major armor repairs. The division never fell below 73% operational availability despite this damage rate. Tanks disabled in combat were typically recovered within 24 hours. Second echelon maintenance performed initial assessment and repair. Vehicles requiring major component replacement moved to third echelon facilities operated by attached ordnance companies. The ordnance companies deserve particular attention. These units, typically 168 men organized into specialized platoons, provided the backbone of the maintenance system. They operated mobile workshops that could be positioned within a few miles of the front lines. Each company included automotive specialists, armament technicians, welders, and general mechanics. These units carried specialized equipment. Portable hoists could lift powertrains from hulls. Welding equipment could repair armor damage. Machine tools could fabricate simple replacement parts when supply failed, but the key capability was rapid module replacement. Captain Robert Henderson commanded an ordnance medium maintenance company attached to 1st Army. His after-action reports provide detailed breakdowns of repair times for common failures. The data reveals the advantage of modular design with quantitative precision. Power pack replacement, complete engine and transmission assembly. Average time, 3 hours 40 minutes, with a 6-man crew. German Panther, same repair, minimum 10 hours, often 24 hours, or more, requiring turret removal and hull splitting. Bogie assembly replacement, complete suspension unit. Average time, 55 minutes per bogie with a 3-man crew. German Panther, individual torsion bar replacement, 4 to 6 hours, requiring special tools and precise adjustment. Track replacement, section of 5 to 10 blocks. Average time, 90 minutes with a 2-man crew using hand tools. German Panther, track replacement, 3 to 4 hours minimum, requiring specialized pin presses. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. These time differentials had strategic implications. A German armored division that sustained 50% mechanical casualties effectively lost those vehicles for weeks. An American armored division that sustained similar casualties could return most vehicles to service within days. This meant American units could maintain offensive pressure while German units were forced to pause and reconstitute. The operational tempo difference was dramatic. 1st Armored Division combat logs from August 1944 show continuous operations for 31 consecutive days. The division sustained heavy combat losses and mechanical failures throughout this period, but maintained attack capability because maintenance operations returned disabled vehicles to service faster than combat removed them. This created a force multiplication effect that military planners had not anticipated. 50 tanks with 80% availability could deliver more sustained combat power than 70 tanks with 50% availability. The Sherman's modular design directly enabled higher availability rates by reducing the time each tank spent in maintenance status. but the system had vulnerabilities. It depended absolutely on spare parts supply. A shortage of replacement powertrains meant disabled tanks waited for components even though repair procedures were simple. Combat consumed components faster than supply could deliver them. Logistics became the limiting factor rather than repair capability. By September 1944, spare parts shortages were impacting operations. The Red Ball Express and similar emergency supply operations focused primarily on fuel and ammunition. Spare parts received lower priority despite their operational importance. Some armoured units began cannibalizing severely damaged tanks to keep other vehicles operational. This practice, while necessary, violated the design philosophy's underlying logic. Cannibalization worked in the short term, but created long-term problems. It removed standardized components from the supply chain. It meant repairs took longer as mechanics searched for usable parts from multiple sources. It represented a failure of the logistics system rather than the maintenance system. The Army responded by establishing forward spare parts depots, specifically for armoured units. These depots stocked high-demand components, including powertrains, bogies, tracks, and weapons. Positioning these supplies close to combat units reduced transportation time and improved availability. By October, the spare parts crisis had largely resolved. Then came the Ardennes offensive. On December 16, 1944, German forces launched Operation Watch am Rhein, driving a bulge into American lines through the Ardennes forest. The offensive caught American forces by surprise and created exactly the scenario that tested every assumption about mobile warfare and maintenance capability. First Army units fell back under heavy attack. Disabled tanks that would normally be recovered and repaired had to be abandoned. Maintenance units displaced repeatedly as the front line shifted. Supply lines were disrupted. The organized maintenance system faced collapse, yet it functioned. 3rd Armored Division maintenance records from the Battle of the Bulge period document extraordinary achievements. Between December 16th and January 15th, Division Ordnance processed 432 disabled tanks. Recovery operations continued despite German attacks. Mobile maintenance units displaced but maintained operations. The echelon system flexed but held. The key was that repairs didn't require factory conditions. A maintenance team with basic tools, spare parts, and adequate security could swap powertrains, replace suspensions, and return tanks to combat even in winter conditions with limited facilities. This capability kept American armored units operational during the most desperate phase of the battle. Staff Sergeant Frank Durbin's experience that December morning typified thousands of similar operations. His crew had no heated workspace. They worked in snow with temperatures below freezing. The disabled Sherman's transmission had failed completely, a problem that would have required depot-level repair for most tank designs. Durbin's team used a portable hoist to support the power pack while they disconnected mounting bolts, fuel lines, and drive shafts. The entire assembly, engine and transmission together, slid out through the rear doors. A replacement power pack from Battalion Supply was positioned, connected, and secured. Total elapsed time, 4 hours 10 minutes in field conditions during winter weather. The tank crew performed post-installation checks, added fluids, test-fired the main gun, and drove the Sherman back toward the front line. The failed power pack went to the rear on a truck, destined for depot rebuild and eventual return to the supply system. This cycle, damage to repair to reissue, kept the maintenance system fed with serviceable components. By late January 1945, the bulge had been contained, and Allied forces resumed offensive operations. The maintenance system had survived its greatest test. Operational availability rates across 1st Army tank battalions never fell below 65% despite the chaos. Many units maintained 70 to 80% availability, even during the heaviest fighting. German armoured units facing similar combat conditions showed dramatically different availability patterns. 9th SS Panzer Division entered the Ardennes offensive with approximately 100 operational Panthers and Panzer IVs. By early January, fewer than 30 remained operational despite relatively light combat losses. Most had been disabled by mechanical failure and abandoned when recovery proved impossible. The contrast highlighted fundamental differences in design philosophy. German tanks prioritized performance. They featured sophisticated suspensions, powerful guns, and heavy armor, but they were engineered to be maintained in equipped facilities by skilled technicians. Field repairs required specialized tools, precise adjustments, and component-level rebuilding. Sherman design prioritized operational availability over individual performance. The tank accepted compromises in armor protection and firepower to achieve maintenance simplicity. Components were designed to be swapped rather than rebuilt. Procedures required basic competence rather than specialized expertise. And the entire maintenance system assumed field conditions rather than workshop facilities. Neither approach was objectively superior. They reflected different assumptions about what tanks needed to accomplish. German doctrine expected qualitative superiority to offset numerical disadvantage. American doctrine relied on quantitative superiority enabled by high operational availability. The Ardennes battle suggested the American approach worked better in practice. The final months of the war validated the maintenance system's effectiveness across all theaters. In the Pacific, Sherman tanks supported operations from the Philippines to Okinawa. Tropical conditions produced different maintenance challenges than European operations. Heat, humidity, and corrosive environments stressed components in ways desert and winter fighting did not. Yet the maintenance principles remained effective. Marine Corps tank battalions maintained operational availability rates above 70% throughout Pacific operations. The modular design that worked in Belgian winter worked equally well in Philippine jungles. Components still bolted in place. Procedures still relied on standard tools. The maintenance system adapted to conditions while maintaining effectiveness. By May 1945, when Germany surrendered, American armored forces in Europe included approximately 10,000 operational Sherman tanks. These represented only a portion of total production. Thousands more had been destroyed in combat. Thousands had been worn out and scrapped. But thousands more had been damaged, repaired, damaged again, repaired again, in continuous cycles that kept combat units supplied with operational vehicles. Post-war analysis quantified the maintenance system's impact. Army Ordnance studies found that average Sherman service life was approximately 3,000 miles before requiring depot-level overhaul, but individual tanks were frequently returned to service multiple times after major component failures. The distinction between vehicle life and component life was crucial. A Sherman might survive 5 power pack replacements, 3 transmission swaps, a dozen bogie changes, and constant track replacement while remaining operationally available. The hull and turret served as platforms for continuously refreshed components. This approach maximized utilization of the most expensive, longest lead time elements, while treating high-wear components as consumables. The financial implications were significant. Producing a complete Sherman cost approximately $44,000 in 1944. Producing a spare power pack cost approximately $6,000. From a pure cost perspective, keeping existing hulls operational through component replacement was far more efficient than building new complete tanks. But the operational implications mattered more. New tank production occurred in the United States and required months of transportation to reach combat theaters. Component production could be distributed globally. Powertrains were manufactured in Detroit and shipped directly to forward supply depots. This reduced pipeline time from months to weeks. The maintenance system also created resilience against supply disruption. A traditional maintenance approach concentrated capability in fixed depot facilities. Disrupting these facilities through bombing or ground attack could cripple an entire army's maintenance capacity. The echelon system distributed capability across hundreds of small units that could operate independently. German intelligence attempted to target American maintenance capability, but found few valuable targets. There were no central repair facilities to bomb. Maintenance occurred, everywhere, continuously, at every echelon, from crew-level repairs to depot rebuilds. This distributed approach proved nearly impossible to disrupt through conventional military action. Soviet observers who studied American maintenance methods during the war noted this resilience with approval. Soviet doctrine also emphasized distributed maintenance, though Soviet tanks were generally harder to repair than Shermans due to less modular design. Post-war Soviet tank development incorporated lessons from Sherman maintenance philosophy, particularly regarding component accessibility and standardization. The lessons extended beyond tanks to military maintenance generally. The five-echelon system became doctrine for all army vehicles. The emphasis on modular design influenced post-war vehicle development across all categories. The principle that field replaceability mattered more than optimal packaging shaped Cold War-era equipment design. Modern military vehicles still reflect this philosophy. The M1 Abrams tank features a power pack that can be removed and replaced in approximately 2 hours using standardized procedures. The Bradley fighting vehicle uses modular components throughout. Even helicopters and aircraft increasingly employ line-replaceable units rather than component-level field repair. The Sherman's maintenance revolution proved that winning wars required more than superior weapons. It required weapons that could be kept operational despite the chaos, damage, and resource constraints of actual combat. This insight seems obvious in retrospect, but contradicted prevailing assumptions when Sherman design began. Military planners in 1941 expected battles to be decided by technological superiority and tactical brilliance. They underestimated how much mundane factors like maintenance downtime and spare parts logistics would determine operational capabilities. The Sherman maintenance system forced a reconsideration of these assumptions. The human element deserves recognition. The maintenance system worked because thousands of mechanics, armourers, welders, and technicians performed unglamorous work with extraordinary competence. These men worked in exposed positions, often under fire, with limited resources. They kept tanks operational through skill, determination, and endless hours of repetitive labour. Staff Sergeant Durbin's crew that December morning in Belgium represented thousands of similar teams across all theatres. They didn't storm objectives or win medals for heroism. They swapped powertrains in snow, replaced bogies in mud, patched armour in rain, and sent repaired tanks back to crews who would damage them again tomorrow. This cycle, damage and repair, failure and restoration, defined the maintenance system's rhythm. It accepted that combat vehicles would break. It prepared to fix them quickly and return them to service. And it designed the vehicles themselves to make repair possible under impossible conditions. The wasteful design that critics dismissed proved to be profound wisdom. Yes, the Sherman used more steel than strictly necessary. Yes, it sacrificed armour protection for maintenance access. Yes, it accepted performance compromises to prioritize repairability. Every one of these wastes contributed to operational availability that exceeded all competitors. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.